Okay, so we're good to go now.
Do you want me to introduce?
Yeah, you can go ahead and introduce.
Okay. My name's Steve Fitzpatrick. I'm trained as a geologist, specifically a hydrogeologist. But through the course of my studies, I had to do, when somebody's in hydrogeology or geology or hydrology, you deal with a lot of forestry issues. You deal with a lot of soil and water issues, of course. And I ended up taking some classes at the Warnell School of Forestry. And through that, and the fact that my advisor, Dr. John Dowd, was a fire jumper as his first career before he became a professor, he got me interested in fire weather, specifically wildfires. And I ended up doing a presentation for a graduate level geography class that I took on GIS, global in GIS. Okay, so I did this presentation and I did it on modeling wildfires with the use of GIS technology. This talk, I made it a little more broad-based to cover science in general, because the GIS fuel talk about wildfire and wildfire modeling is a little too specific. We're going to touch on modeling too, because of course modeling is very important in science. You have to use it. Wildfires, or wildland fires as they used to be known, are defined as any uncontrolled burning of vegetation in the countryside or wilderness. Now, wildfires are set apart from any other kind of fire by their extensive size or increased speed or rate of spread, which is fueled by wind to a large part. You get a 30-mile-per-hour wind, you can have a fire that goes 30 miles an hour. You can have a fire that goes up a hill faster than across level land. They're very dangerous that way, and it's part of it's because they're updraft. Hot air rises, and it fuels the fire. It causes the fire to spread upwards. The potential for sudden change in direction with wind direction. The ability to jump gaps such as roads, rivers, and fire breaks. And it's going to happen because there's enormous heat. This enormous heat can cause these columns of hot air to send out fuel materials, which can spark on the other side, especially during a drought. Now, wildfires are also characterized in terms of the cause of ignition. The physical properties such as speed of propagation, the combustible materials present, and the effect of weather on fire. The fuel is very important, especially when you're modeling wildfires. With fuel, it's often your underbrush, which becomes dried and desiccated. Once it dies, you gather up enough underbrush, you get enough dry conditions, and you just light it with maybe a lightning strike, and you have a wildfire. Okay. Fire occurs due to combustion or rapid exothermic oxidation reduction reaction. That's exactly what fire is. It's very rapid. Fire itself is gas. Gas. Okay? Superheated gas that emits heat as well as light. Fire begins with fuels that are subject to the right amount of heat and the correct amount of dehydration. Dehydration is extremely important because this is where you get a lot of your forest fires down in South Georgia. In the drought period back in 2007, huge fires down near Waycross. That's because of dry conditions. The water is just not in the air, and the water helps to attenuate any chance of combustion. The converted products of combustion are often as combustible as the fuels, since these materials are converted to char. Now, char is your black woody material that's left behind. It's that black stuff you see in a campfire. Very combustible. It's pure carbon. The speed of the fire front is often dependent on wind, velocity, and all these conditions create a field of study known as fire weather. I mentioned my advisor. He actually studied under a gentleman who I believe worked out west, and his specialty was fire weather. So fire weather is a field. Wildfires require dry conditions. The greater amount of water present, the less likely for a fire to begin. Fire requires heat to begin and a continuous application of the correct amount of heat to continue. The heat creates dry conditions. It's a constant positive feedback. At a fire front, as it's advancing, a really, really raging wildfire out in the wilderness, is going to have up to 1,000 degrees Fahrenheit in front of it of heat actually possibly convecting off of it in the air. This heat will instantly dehydrate anything. All that instantly dehydrated material that fuel needs is just a little spark, and it comes up. So you actually have a sort of advanced warning system for fire there that's naturally built in. Fire requires fuel. Fire is a chemical reaction. Without this fuel, fire cannot continue. When you run out of fuel, fire gets to, let's say you're in Arizona, or maybe Nevada's a better example. Actually, Utah's a better example. Okay, fire gets right up to rock, can't go any further. It's just about that simple. Fire requires oxygen. It's an oxidizing reaction. The wildfire front, the moving line of combustion, is a forest fire. In a forest fire, acts to sustain a wildfire. Like I mentioned, those temperatures, 800 degrees centigrade, you get enormously hot. Air rises as it heats, and it creates strong thermal updrafts, which can lead to fire, what they call fire stacking. And this is where you get fires that literally go straight up. And these updrafts will go to the top, to the canopy of some of these pine forests, and a tree will just go up like a match. It also goes uphill. Like I mentioned, these things can go 30 miles an hour uphill. You can't outrun them. Okay, what are the causes of wildfires? Well, wildfires originate through human activities and natural processes. Wildfires are a natural process. They need to happen. We'll go over that in a minute. But here's a sort of a graph. I think this was done in the Northwest. So each region has its own different, set of needs. But this is pretty much how it occurs. Most of your campfires, your wildfires are going to be arson. There's a large portion of these are arson, believe it or not. I don't know who's setting these fires, but arson always is a big slice of the pie. Children, okay. Railroads, I don't know how that happens, but railroads. Debris burns. People are burning in their backyard. Spark gets off. This is probably it's probably very, very relevant to California. Okay, because California has a big problem with wildfires because it has these dry woods in that Mediterranean climate that go right up to houses. Okay, and then smoking, people throwing their butts out. Campfires and lightning. Lightning, surprisingly, takes just a small part of the pie, but lightning strikes are the most common natural occurrence for wildfires. And this is where wildfires are actually necessary.
So, and question,
No. Go ahead.
Arson, this is when somebody's burning like a building with insurance, but they're not trying to burn the forest.
I don't know. What I'm thinking.
I think I've read in California where they're trying to burn the forest.
Yeah. You can own land, and maybe you're going to get some insurance off that land. So.
Or just plain mischief.
Yeah.
Which is every bit as devastating.
Yeah. Exactly. Okay. The forested ecosystems need fire. Wildfires are necessary. They're natural processes. And fire reduces the overaccumulation of plant growth, specifically undergrowth. It's that undergrowth, you accumulate a lot of it, you have dry conditions, you just have tinder, and it'll go up. Okay? Also, this underbrush inhibits the growth of other species. You get rid of it, and you can allow other species to proliferate. Forests naturally burn. They have to. Okay? Fire can stimulate growth and the reproduction of some plants and require it, and it also makes room for habitats. For example, there's a tree out west called the lodgepole pine, and the only way that it dislodges its seeds from its pine cones is by being heated. And forest fires heat these pine cones, and the pine cones drop their seeds. This is how the lodgepole pine proliferates. There's also something that the Forest Service does called using prescribed fires. Okay, and this is where they purposefully set the forest on fire. Major reason for this is that when undergrowth dies, it becomes dry, it becomes a fuel. Also, we've gotten so good at, believe it or not, we've gotten so good at preventing a lot of forest fires, we actually allow for this underbrush to proliferate where it naturally wouldn't, okay? Because we're preventing a lot of fires. Well, this underbrush is what causes a lot of these is a fuel and causes, sort of an exacerbation of the process. An overaccumulation of the fuel increases the chance of out-of-control wildfires. Another reason to set controlled fires is to prepare. There's several other reasons. One of the reasons is to prepare sites for seeding and planting. You want to clear the land to plant. Forestry does it, I believe. Dispose of logging debris, which is actually very relevant to Georgia because timber is one of our biggest, if not the biggest industry in Georgia. Improve wildlife habitat, manage competing vegetation, control diseases, and it's a good way to help recycle nutrients through. The U.S. Forest Service actually has a pamphlet which they use called A Guide for a Prescribed Fire in Southern Forests. I use it as a citation. That's what that person's doing there, setting a fire. In 1910, Congress appropriated funds to aid in wildland fire suppression by the National Forest Service. This sort of started the whole cycle there. And we're talking about controlled fires. Also, the U.S. Forest Service spent $1.4 billion for fire suppression in 2007. Some of that was Waycross. Some of that was what was going on in South Georgia. Urban areas continue to encroach on wildlands, and we're seeing wildfires affecting people in their homes. We're seeing businesses now being affected on a larger scale because development is encroaching on wilderness land. This is happening in North Georgia right now. Okay, and here's a map, chloropleth map of, chloropleth map is a map that shows statistical data over a predefined area. That's the definition of a chloropleth map. There's sort of the aerial distribution of reported wildfires for that month, 2009, and you take this and you can sort of think forward to the next month and know, okay, we have a danger here. Once again, oddly enough, South Georgia, you don't think of it as a big wildfire. Of course it's not. You get a lot of these fires in these regions. The West has a particular problem with it. Montana, there's been some incredible forest fires there. The Man Gulch fire, we'll go over that in a minute, back in 1949. Each area of fire danger is denoted from low to extreme. High is part of Georgia, so there's generally a high danger level depending on the amount of moisture in the air, depending on the precipitation that's occurring at the time in South Georgia. Okay, and then the long-standing wildfires back in the summer of 2007. I remember them going on for a few weeks. I was in Colorado at the time, but I was paying attention to the news, and they were there for a couple of weeks. Okay, well, to understand fire, you have to do fire research, and this has been going on for quite some time, backed by the U.S. Forest Service. Okay, the cost of unchecked wildfires would be considerably higher, especially in terms of environmental costs, were it not for prevention techniques. One of the pioneers was Harry P. Gisborne. That's him right there. And he developed a simple model known as the fire danger meter, which continues to be used today. He developed it in 1931. In 1949, there was that fire that I mentioned near Helena, Montana, called the Man Gulch fire. It was an enormous fire, very devastating. Well, Gisborne decided he wanted to research this fire to a T, and he spent all of his time out there putting forth basically a Herculean effort, and it killed him. He died from the efforts, possibly from smoke inhalation too, of his research into this fire. And the data he collected like a mountain of data, and it continues to be used today. We use it today. People that developed models back in the 70s of Rothermel, we're about to talk about Richard Rothermel, used his data. It was so precise, and it was so huge, and it was so detailed, and it killed the guy. The data he collected helped a decade-long intensive research. Ultimately, Richard Rothermel and his team in 1971 and 72 developed the Rothermel model, and it's a very robust tool. After Rothermel, a researcher who's a very astute mathematician named Frank Albini took it further and created another tool, a series of graphs called nomograms.
This is a model of how fire burns or how the danger is?
How it propagates, how it burns across an area, where it's going to be, where you think it might be.
Also prediction of hazard.
Yeah. So you model it and you go, okay, that fire has a great chance of crossing that divide there. So and this is where the fire, people fight fire to get out there, and they'll put their lines down and try to prevent the fire. This is a danger meter. It's fire danger meter. See, it's really simple. It's just a sort of a little dial-up graph there. It's a simple model for fire estimation. It's a slide rule-like device. It takes into account parameters and variables such as fuel moisture, condition of vegetation, wind velocity, a few other parameters. There have been a lot of modifications. People are still using these, and they're making new ones. So there's been a lot of variation. There's been a lot of work done on these, that you can buy them online. The fire danger meter is a type of model, okay? Models are really important in science, because, especially in natural sciences, because like biology, geology, astronomy, forest science, soil science, all that, because they allow you to understand processes before and after the occurrence, and they also allow you to make predictions. Something like this, forest fire prevention, you want to make accurate predictions. And that's Richard Rothermel. In 1972, Richard C. Rothermel, as a research engineer for the USDA, introduced a mathematical model that was applicable to the prediction of both fire spread and intensity in forests, brush fire, and grassland. So yeah, it's mostly a fire spread model. Model is used today, and it's been upgraded. Very mathematically astute people like Frank Albini have done further derivations on it. Taken some of the functions that Rothermel came up with and done further derivation and things like that. But a lot of models employ remote sensing, and a lot of the models, rather than do an analytical solution means you're using calculus. A lot of these, for ease of use, use a finite difference or finite element type background, which is more of what they call a numerical model. And a finite difference, take the difference of the first and you get to the next. Finite element is actually a lattice work. It's a grid, and it uses matrix equations. So I think they can get pretty complicated. Okay. But also using something called cellular automata, which actually is related to finite element, and there's even neural networks that they're developing to sort of model the way these things behave. Richard Rothermel's mathematical models for the prevention of fire spread assume very few parameters. And the parameters of importance involve the characterization of the fuel itself. He was very focused on the fuel, what the properties of the fuel were. Apparently this worked. Apparently for the conditions he was dealing with up in the Northwest, this worked. So within Richard Rothermel's model, the physical and chemical characteristics of the fuel are key. So you're dealing with the fuel a lot. The concept is that of a fuel model wherein parameters of wild fuels are necessary for input to the model are characterized and tabulated. So it's a fuel-based model. Okay. Inputs are used to predict fire spread and intensity, and it is founded on the concept that fuels have inherent characteristics that are predictable. You can take your fuel, whatever type of underbrush it is, and depending on the application of heat, dehydration, and whatnot, you will get a fire. Okay. Oh, bummer. All right. Oh well. Well, there's one page of his. This was another page. It's from the actual pamphlet, which I found online. The main equations of the model relate to the rate of fire spread, feet per minute. They're using English. The forest guys, they use English. They don't use metric. And fire intensity, which is British thermal units per foot square minute. And these were derived and integrated into a series of mathematical functions relating to such characteristics as moisture and mineral damping coefficients, slope factor, and wind coefficients, all centered on the fuel. And there's his basic equation there. R is the rate of spread of the flaming front. IR is the reaction intensity, and it's a whole other series of functions defined as fire intensity. That, epsilon, I think that's what it is. Proportion of the reaction intensity of heat adjacent fuel particles to ignition. This is what I was talking about. That's why it's such a powerful factor. That heating front that's in front of the fire, that up to 1,000 degrees that can be in front of the fire front is very important. Okay, and then there's BW. I said W should be lower, but you get it. Dimensionless multiplier accounting for the effect of wind in increasing the proportion of heat that reaches adjacent fuels. Okay, and then there's BS. It's another dimensionless multiplier, and it deals with slope rather than wind. So these two are kind of very similar, and you notice that they occupy this similar place in the equation. That right there is the oven dry fuel per cubic foot, so you're taking into account volume. And another dimensionless number, that's a big one right there, accounting for the proportion of a fuel particle that is heated to ignition temperature at the time flaming combustion starts. And there's a caveat here, which I find interesting. That's near unity for fine fuels, but it asymptotically decreases towards zero as the fuel size increases. So you're dealing with almost a surface roughness. You know, fuel can be a log, okay? So that's a large sized bit of fuel. But at the other end of the spectrum, the fine fuels are your particles. When, maybe underbrush has been dried for so long, it starts to disintegrate and almost turn into a powder. That's your fine fuel. And then QIG, the heat of pre-ignition. And once again, that can be part of the fire.
It's most of sitting on the ground, it's not the trees.
It can be the trees. It can be the trees. Often what happens is you get an over-accumulation of this brush, okay, and it sort of adds to the volume. And this is volumetric dependent, and that's what starts it. And then once you get that enormous amount of heat, and once that fire gets going, that's when you get the conditions where you get updrafts and you get all of these conditions, which adds to the weather, the fire weather of this whole thing.
Yeah, that's where particle size evidently comes in, because fire weather is going to create a strong updraft when winds in from the side, like in front of the fire, that can bring in dry leaves, broken dry leaves, and of course those fine particles are virtually explosive.
Yeah, and they're so easy to get a wind to carry a 10-mile-an-hour wind. You get disintegrated leaf litter, just carries it everywhere. And once it started sparking, it's going to catch tinder on fire. That's why these things are so dangerous. Okay. There's Albini's nomogram. Albini was a brilliant mathematician. He's got pages of derivations and integrals that went into this kind of thing. I'm not going to go into that here, but needless to say, he took Rothermille's equation and his findings and refined them. And around 1976, he came up with a nomogram. Now, a nomogram is actually used for a lot of other things, apparently. It's another type of model that is used to graphically depict complex mathematical relationships, and those are complex, relating to natural phenomena quickly and accurately. So you get Albini in here, and this is something he did by hand. He did this himself, and he gave this to the people that were fighting the Hell-Roaring and Shoshone fires, which I believe were going on in 76 or 77. He gave it to them, and they were able to see where they were. You have these series of curves of predicted models here that you can pinpoint where, and there's the behavior of the Hell-Roaring fire right there. It has a certain rate of spread, certain unit energy, square. And it's flame length. How long, what's the length of these flames? You know, how high are they reaching? Are they reaching up to the canopy? There's the power of the fire, just the sheer power. And he graphed it all together in a lot of complex equations. And he gave it, literally, it's a site-specific. This was for this fire, and he gave it to the people who were fighting the fire. Okay, the models are continuously refined for specific use. Models aren't perfect. I read a paper written by some researchers in Greece that found that Rothermel's equations didn't quite work for them. Different conditions. Greece is a bunch of limestone that's been carved up. You know, there's not this dense underbrush like there is out west. It's a completely different area, so it didn't work for them. That's the way it is. It's natural science. It's never perfect. Science itself is based on a rigorous system of critical review. So, part of it. Okay, one of the ways you input information into a model, like Rothermel's model, is you use remote sensing. Nowadays, you can find where a forest fire is using satellite technology. Today, wildfire management is a problem on a global scale. Satellite remote sensing of fires continues to approach higher levels of accuracy and resolution on a global scale. We're about to look into that. Despite this level of visibility, it's uncertain whether variability in land cover type, surface temperature, and fire regimes will permit the use of measured global temperature and reflectance threshold, meaning there's an area of uncertainty, you know, because you're trying to see an infrared signal that might not be a fire. It might be something else. So you have to correlate it with ground fact, ground truth, as usual. Trace gases and particulate species monitoring are of prime importance on a global scale. You can get a spectrographic analysis for maybe something like MODIS of what kind of gases you have. I mean, you can see a fire and it's smoke because you can detect the amount of carbon monoxide and carbon dioxide that's in the air around it. And particulate species refers to particles in the air. Also can refer to aerosol-like particles that are thrown up by fires and a lot of other natural phenomena. Due to advanced fire monitoring sensors such as MODIS, reliable information, we can get pretty good information. Once again, you need ground truth. You have people on the ground that are confirming this. Okay, and the caveat is it's got to be coupled with data gathering, and the Forest Service does this. Okay, now this isn't really fire from space. Okay, this is a colored and sort of time-dependent depiction of where fires occurred within, I think it's within a month. I mean, it doesn't look like that. This is like if you're looking at a picture of the Eagle Nebula in outer space. Well, they've colorized it. Well, the people that do remote sensing with MODIS colorize things too. You do that all the time. But this gives you an idea of how widespread. People clear cut, especially in the equatorial regions, through the Amazon. Of course, we're having a problem with people getting rid of forests in the Amazon. People are clear cutting using, over on the other side of the globe, but if South America was here, you'd see a lot of red on it too. People are clear cutting using fire. People clear cut the Congo with fire. There's something going on here. It's either natural or clear cutting. People clear cut in India. Clear cutting is a widespread practice. It's done everywhere. And it's not clear cutting, it's burning to make work. It's clear cut, we'll do both. The Farsight is a model, it's one of the models. There's another type called Behave, and Farsight's the one that's used mostly by the U.S. Forest Service. And it's a finite element model, not a finite difference model. It uses polygons over aerial space. It's called Fire Area Simulator, Fire Behavior and Development Finite Element Model used by several agencies, including the USDA Forest Service. It utilizes Huygens principle of wave propagation, actually. They sort of added that into it, which is interesting. The fire fronts are seen as the front of a wave ellipse in this model. So they're modeling it as a wave ellipse. And if you think about it, there's convection going on there. It makes sense. It makes use of digital elevation models, which is odd because those guys in Greece said the elevation was not working at all. Okay, like I said, they're not perfect. GIS is used for slope, aspect, and elevation things. So you can use, you get your signal, you know, infrared signal, and then you can use the actual, what MODIS does, you know, sort of visually imaging and altitude imaging where this fire is, and you start putting your inputs in that way. You get a long, you get a long list of data in your computer, and you start inputting into the model. Data sources must be entered manually, and these include existing vegetation maps. So they're probably taking USGS, you know, 7.5-minute maps, putting it in there. That's what they're doing. Use satellite imaging analysis along with ground truth data. Again, clarify it on the ground before you send some guy out there to take a look, guy or gal out there to take a look. Aerial photography, a lot of what's done is people will fly planes over these areas, and they can gather data this way. In fact, most maps that you have that you can get at like a map library, like the one on UGA campus, are based on flights rather than satellite. The historical data, there's tons of them. FarSight supports data in ASCII format, and you can plug it into 2D ArcView if you're using ArcView. So. Okay. Let's see if this works. This is an animated GIF. Can I?
So it's supposed to be animated?
Yeah. Can we?
I'm not sure if it'll do that through Windows.
Well, I can explain it.
Yeah, maybe you can.
What you see this little circle here? Okay. That's where the fire started. Okay, this is a model built from FarSight, using FarSight.
Maybe you can use the cardinal directions for people on the online.
Yeah.
Like which circle do you point to? In the center?
Right.
The white outline.
And it's gonna propagate this way. And if this was working, you'd see it sort of like, hard to explain. Oh, like a stain of water. Like if you take a white tablecloth and you blot it with some wine or something, and it starts spreading out. That's not exactly, but that's a lot like what this looks like. And it shows you over time, you get this clock here. Once you've modeled it, what the probability of this fire, what probability it has of being here in, let's say, 20 minutes versus here. Here, you see a lot of rock. You get a body of water somewhere. It's not going to crop it that readily, but you have some vegetation and you have certain conditions, say it's real dry. Look at all that forest. Well, it's going to be way up here versus here in maybe 30 minutes. That's how FarSight works.
Steve, is this where we enter the website?
In government. Thank you. And I've seen it work, and it seems to make sense. And this is all done, before any fire occurs, or maybe after a fire occurs, to see if your ground truth matches the modeling data. You compare the two. Okay, MODIS is one of the satellites where we get information for fire modeling, provided by NASA, and two satellites, the Terra and the Aqua satellites. MODIS scans the entire planet every 1 to 2 days in 36 discrete spectral bands. And MODIS is used for a lot of applications, not just fire, fire prevention. It's a whole host of GIS applications that it's used for. MODIS data is highly useful for inputs into a variety of geographic, climatological, hydrological, and geological models, including FPM, fire prevention models. Fire prevention models, another type of model. There's more than just FarSight. There's Behave, FPM, FarSight, a bunch of others. So it seems that MODIS does a lot of sort of earth science-based imaging, geological, hydrological, climatological, and geographic. Okay, there's a MODIS image, and there's a slices it takes, and it covers the planet. And I don't know why it's variable, but it covers the planet in 1 to 2 days, both satellites. And there's the URL.
Is that the one where we want to go to?
Yeah, let's go one more slide.
Okay.
That's it, okay. Active fire map. This, you can get online, this URL, which you're about to get to, and see where fires are occurring. This is what MODIS is telling us right now, where these fires are occurring.
Yeah.
Thank you. Thank you. And we'll take a look at where those are right now. Okay. Nice. Okay, what do we have? We don't have anything. Okay. Kind of similar to the one we saw. There's one here, Ranger Complex in Arizona. Florida. That one in Florida. Yeah.
I clicked on it.
That's fine. No. Let's look at it. Okay. Cause lightning. You see, we've got people. You're imaging it, and then you've got people on the ground going out to take a look at it. You've got somebody that reported it as lightning. Okay. The fuel. Here's the fuel. The fuel's predetermined. We've already determined what the fuel is. One short grass, timber litter. Very interesting. Okay. Can we look at another one?
Sure.
Okay. Let's see what's close to home.
Florida.
Yeah. Let's see the one we can go to right now. In Kentucky, okay. Caused human. Oh my gosh. Okay. Somebody caused that. You got medium fuel. I suppose medium fuel is size dependent. A medium-sized fuel, whatever the metric for that is, probably small timber, wood, something like that. Yeah, let's take a look at Florida.
All right.
Oh, cool. Okay. It's gonna be interesting. Marion County, they don't know the cause. They haven't figured it out.
It's not John Bronson.
Yeah, no, he's the guy on the ground for it. Litter and understory. Understory is anything below the lower canopy in the floor, of course. Medium.
Pine Castle bombing range. I wonder if the Air Force did that to themselves.
Oh! Maybe so. Maybe so. And then the causes, it's the Air Force, they don't want to tell us. Just keeping it hush-hush, you know? Yeah.
Classified.
Cool, okay, see, you can find out so much, you know? MODIS is telling us a lot, and you can get on the website.
Now, when you see fuel here, this litter and understory, how finely do they model that? Like different kinds of litter, oak versus sweet gum versus pine litter? I mean, these have very different combustion.
They do. You have to consider the type of litter, the type of plant. Wood is cellulose material, has all sorts of different properties, different fibers, you know. There are different water contents, too, and moisture.
Pine litter, dry pine needles have remains of resins in them that burn. I mean, it's almost a hydrocarbon.
Yeah.
It's very good.
Exactly.
When we looked at Arizona, it was talking about grass. I mean, how finely do they model the type of grass that's burned?
Apparently, it's really important. So I
would think so.
I would think there's a roughness coefficient.
Worldwide, you've got 20,000 species of grasses, and they probably all have different combustion characteristics.
You're probably looking at the actual size, the physical size, or you're looking at volumetric content because you get a volume of this stuff.
Right.
And I would almost imagine that there's some sort of surface roughness coefficient for this kind of stuff because it's really important.
I mean, in prairie systems, you don't have just pure grasses, but you have grasses intermixed with shrubs. At lower sites, you would have more moisture than you would have over ridge tops.
Yeah, exactly.
I imagine it gets extremely complex.
Very complicated, and that's why Rothermel created a fairly simple model. And somebody like Albini came along and added so many more parameters and state variables, too. The modeling, you have your parameters, and you have your state variables. The parameters basically say the same. State variable is just what it says, it's a variable. It's dependent on other conditions. It's functional, you know. So, yeah. Can we look at that again?
Okay, sure.
Just see where there's more fires. Okay, none in California. Let's see the one in Louisiana. That's kind of interesting. You don't think about that with Louisiana, but Louisiana actually is a very well-forested state. Lightning, okay. Longleaf, loblolly. We got a lot of longleaf and shortleaf pine in South Georgia. Blue stem, hardwood timber, yapon. Yapon is the type of plant that grows, I believe, in the barrier islands. You got some in like Sapelo Island, Jekyll Island. And so, okay, lightning caused this. So they got accurate. Team leader, there you go. You know? So, I mean, this makes fire prevention, actually, our fire prevention system in this country is very efficient. And once again, because you need controlled burning, it's too efficient. You need to actually get out and burn that sort of that understory, that undergrowth, because it'll build up and cause out of control fires.
But if only 7% of the fires are caused by lightning, which is the only natural source. People. And it would seem like there are enough fires that we cause.
Yeah.
Is that not true?
Well, and then there's that huge portion of the pie that's arson, you know. That's semi-creepy. I mean, you don't think that people are out there purposefully burning natural lands, you know, but they are.
Well,
maybe
in Colorado, was it last month or the month before, there was a big fire near Boulder. Wasn't that set by the fire department that was burning debris at his house?
Oh, okay.
And his house, among many others, burned down.
So, human quality, you know. Yeah. Put out your forest. Put out your forest fire. Put out your campfire. You know, it's the old Smokey the Bear type, you know, message. But okay, can we get back to the?
It's not pick up the prescribed fires we were talking about?
Oh, no.
Like control it?
Right. The prescribed fires are, you know, the idea is you control them, and they're not. I believe they're not done. If there's a lot of wind, they don't do these things. I mean, they don't want them to get out of control.
I've seen places where they've been done, and yet usually they make sure it's a dewy, foggy morning before they set the fire, so it's not going to go.
I've seen them too. I've seen them. They're kind of like where you drive down through South Georgia and see these places where the fire just stops. They just stopped it, you know, and because they meant to put that fire there. And if you end up going to school at Warnell, you know, they'll probably have a class, you know, how to do prescribed fires. You get to go out in the woods. Okay, I guess the next one?
Ready for the citation?
Sure. These are my citations. I have a paper that I did for this too, and so a lot of this stuff. And there's Merle Dixon's, you know, a guide for prescribed fire in Southern Forest. Dale Wade just, it was recently, it's been added to, that, you know, they've come up with new techniques. But it was originally published in 1989. You can get it online, U.S. Forest Service. And there's Rothermel's original paper. He did it at that place in Missoula, Montana. Is where he was stationed. So okay, there's the citation, and we'll last slide. Any questions?
This is notice that the infrared imager.
It's got a lot of instruments on it.
This is 32 bands. Sounds like it's got like 32 different infrared filters or something like that.
It does infrared. I think it does ultraviolet. It does a lot. I mean, all the USGS, Forest Service, a lot of people. You know, I guess for satellites, you reserve time or you reserve space in satellites. You have to you know, sort of fill out a form to NASA, I guess, and get space and time. And then you know, it's what these people do. Because there's people that are getting grants. What's that?
Submit a proposal for.
Yeah. And then once you get the proposal, you have time. You have space on that satellite. And it's sort of a subscriber service as far as I understand. I think it is a subscriber service. You can get information on it. So it's a good thing. It's a good thing because you have the eye in the sky up there that can see broad areas that we can't see on the ground. A forester, a forest ranger can only see line of sight. Once you get that broad area, then you get a human to go down there and get ground truth, take data, and you can take actual temperature data, specific temperature data. You infer it up there when you see an infrared signal. You kind of go, okay, it's got to be in this temperature range. You don't even know if it's a forest fire or a fire or whatever it is. You get somebody on the ground, take specific data, and you correlate the two. You've got to compare your model to ground truth. That's what you have to do in general. Okay.
Well, your model or models you've talked about all apply to wildlands, national parks, forests, grazing lands.
Mm-hmm.
Is it applicable too to urban areas? I've been thinking about this since you first gave us a definition at the beginning. You know, these are out-of-control fires that can jump roadways, they can jump rivers. It sounds like the Chicago fire in 1871.
Yeah.
Burned, 4 square miles? And
I would hope that
jumped the Chicago River at least twice.
I haven't researched urban fires. They're, of course, probably of greater concern to all of us.
Yeah.
I would imagine there are pretty technically minded people at work. That's maybe something we can look up.
You know, I know a lot of urban fires are pretty well controlled, but then, was it in Detroit a couple of weeks ago, there was whole blocks that burned?
Mm-hmm.
Of course, a lot of those houses were vacant anyhow, because Detroit has such high unemployment, people moved out.
It's like Baltimore. You go through Baltimore, and there's row after row.
Right.
There's nobody there.
Bad to see.
Yeah, I would imagine that somebody's modeling for urban, because you can model microclimate in urban, obviously, from having taken geography courses and climate courses. There's a thing called microclimate. So this is we're in a microclimate right now. You go in downtown Atlanta, you're in a climate. Urban areas impact anything outside of them. We have an urban heat island. Heat sent up. It's the summer. Here comes some rain. Picks up the heat, updrafts, and you get a thunderstorm over in Gwinnett County.
Oh, I wish.
Right. Yeah, see, it's getting dry now.
I live near Norcross, and, you know, I've got a wooded lot. Much of my neighborhood is wooded, and, God, I see that all it's going to take is some kid playing with a match, and the whole neighborhood's going to go off.
And here comes Halloween, too.
Yeah.
Well, that's sort of what my question is about, you know, how would you rate the chances, and we have the fire weather that we have going on right now.
Mm-hmm.
You know, we had months of drought, maybe just, you know, a little bit of rain every 3 weeks.
Well, it would be your relative humidity, and sort of relative humidity patterns. You know, for how many days on end do we have relative humidity down in the 30% you know, and the more days like that, I'm certain there's somebody at the U.S. Forest Service who's looking at it, you know, tabulating the data and making charts and going, wow, we're getting into a drought again. Because it rained recently, but it just didn't rain enough. Now, where I live, just a little sort of spurt and then dry the rest of the time. I mean, and the gardens are, you know,
Well, yeah, my friends are like perking up for a day and then.
Yeah, they're like, come on, give us more. Yeah, exactly. Yeah,
That map, you showed a map of fire hazard for the whole U.S. or something.
That was for 1 month. They make those.
So where's what that based on? I mean,
reports?
What do you mean?
Reports, like, you know.
But I mean, that's the hazard, right?
Mm-hmm.
I mean,
They take it from
to the water content of fuel or something like
no,
that?
just where they report a fire, and they do that for the whole month, and then you go, okay, there's a likelihood of the next month. You know, you use that map for the month. The next month, the month you're in now, from the previous month, because conditions don't abruptly change from month to month. You know, nature doesn't have a calendar and goes, okay, it's January, we got to stop this. You know, so you use it to predict. It's another prediction tool. You know, you use the previous month's data for this coming month. You know, that's your likelihood, depending on what kind of weather you might be getting. And things change constantly. You know, this is why it's good to have satellites up there, because you can monitor these changes, you know, minute by minute.
Steve,
That's why I was
Yeah,
asking,
yes.
the Weather Channel app on my phone.
Oh, cool.
Fire weather watches about something.
Really?
Yeah.
Here?
Yep.
See?
North
We're-
Central Georgia.
We're in trouble.
Yeah.
Yeah, I don't know if we're in a drought yet, again, but, doesn't rain much soon. We're gonna, we're gonna be there again. I mean, out of an enormous drought, caused a lot of damage. I mean, Lake Lanier just turned into a puddle, What's gonna happen again? I don't know. So, it's good. Apps are good. Apps are good. Okay, is there any more questions?
No,
Okay, well, thank you for coming.
welcome. Actually, it looks like our next speaker will be Fred. I haven't scheduled anyone in between so far, but, Fred will talk on December 1st about the far side of the moon. I'm trying to get someone in between, but we'll see if that happens or not.
My thesis is stressing.
Well, thanks again for
You're
coming
welcome.
today.
You're
and
welcome.
See you next time.
Yeah.
All right.